This is a quick video just to give you the basics of relative velocity, and at the end I'll talk a little bit about something called the principle of equivalence, which is kind of a big deal. Right now, you're probably at rest. You're sitting in front of your computer and you're watching this video and you don't feel the wind rushing through your hair or see anything passing by you. So it makes sense to say that you're at rest. But the thing is, we're on planet Earth, and planet Earth is constantly moving. It's spinning on its axis, it's moving around the sun. And you may say, okay, yeah, fine, but it's not really moving that fast. But the thing is, the Earth is going 67,000 miles per hour around the sun. It's moving very fast, at least relative to the sun. So there's that word relative, which I'll clear up in a second. The thing is, we don't feel how fast we're going. What we do is we notice things moving relative to us, we see their positions changing, and we infer motion as a result of it. So you've probably heard head-on collisions are really bad things because if one car is going to the right at 10 and the other car is going to the left at 10, then they crash into each other at a relative speed of 20 meters per second. But what is it that's going 20 meters per second? Certainly neither car is going 20 meters per second, or are they? So if you look at how I've labeled things, you'll see VCG on the left. That's the velocity of the convertible relative to the ground. On the right, I have VSG. That's the velocity of the sedan relative to the ground. And if you look at the bottom, I've got VGG, which is it's kind of silly. It's the velocity of the ground relative to the ground. So as far as the ground's concerned, it's not moving. It has a speed of 0. But if we don't feel our motion, then we could just as easily, instead of taking it from the point of view of the ground, take it from the point of view of the guy in the convertible. He doesn't think he's moving at all. In fact, he thinks that the sedan is rushing at him at 20 meters per second. It has to move that fast because he notices its position changing relative to him, and so the sedan has to make up for the position changing that he was doing earlier relative to the ground. So it's going to go at 20 meters per second. And meanwhile, he sees all the squirrels and rabbits and stop signs and stuff also moving toward him at 10 meters per second. That's his perspective. We could swap it up and take it from the sedan's perspective too. Now from the sedan's perspective, the guy in the convertible is going 20 meters per second to the right. And now the ground is rushing toward him at 10 meters per second. These are all equally valid viewpoints, and the numbers are totally different. Let's examine this from one more point of view. If you remember from one of the last videos, we took a look at a coin flipping. And if you stand on the ground and you flip a coin, it's pretty clear what's going to happen. The coin's going to go up and it's going to go back down. But we also saw that in the last video, if you flip a coin in a car that's moving and we ignore wind, the coin does pretty much the same thing. It goes up and it goes down. Well, now we know, because of relative motion, that the guy in the convertible can say that it does that because I'm at rest. I'm not moving. It's the guy on the ground who's moving toward me. That's because we can't tell how fast we're going. If you remember in that last video, we had this crazy motion that we showed that the coin had to make because the guy is moving, so relative to the guy on the ground, the coin makes this crazy parabolic motion. But of course, if the guy in the convertible feels he isn't moving, he sees the guy on the ground make the exact same crazy parabolic motion. This is probably a little less obvious. This is some pretty complicated motion we're getting out of just switching perspectives. So let's keep examining this. I want to imagine this same guy flipping a coin standing in an elevator. On the left, I've got the view from the elevator. In other words, he thinks he's going to be at rest. And then on the right, I've got the view from the ground. So from the ground, of course, the elevator is moving upward. But from the elevator's perspective, the ground is moving downward. So he flips the coin, and however hard he pushes the coin, he gives that coin some initial velocity, which I'm going to call VI. And in his perspective, that's it. That's all the coin has. Of course, if you're watching from the ground, you see the extra speed that he gives it, but that the total speed of the coin relative to the ground, that's that VCG, the coin relative to the ground, is the initial speed he gives it plus the speed of the elevator. It's extra. Well, let's put a little math to this. So in both cases, it's the same kinematic laws, except that if you notice, the speeds are different because they're relative speeds. So in the case of the elevator, the coin leaves his hand and arrives at his hand. He's not moving, so the distance between those two events is 0. Meanwhile, from the ground, it starts in his hand and it ends in his hand, but his hand has moved upward a distance vt during that time. So let's plug this in and see what happens. We get two equations, which I've just plugged in, and then if I solve for the time is identical. So they may not agree about where the coin is and exactly how it's moving, but they agree that it takes the coin about the same amount of time, and they agree more or less that the forces acting on the coin are the same. They say, okay, well, the coin is subject to Earth's gravity at 9.8 meters per second squared. This makes sense. We can't tell how fast we're going. The laws of physics look exactly the same. What happens if we accelerate? Something strange. Let's see. So here we are, view from the ground again. And from the ground, we see accelerating upward. That's what the elevator is doing. So as it accelerates upward, we write the same kinematic law we wrote before. The coin has the same speed relative to the ground it had before. The difference this time is that the difference in position, so it starts in his hand and it ends in his hand, but remember his hand moves not only VT now, it's accelerating too, so it's going to move an extra bit upward. Well, we do a little bit of math, we write this down, and we solve for the time. The time's a little different than last time. In fact, it's going to be a little bit less time than before. The denominator has gotten bigger. And that makes sense. He flips the coin up, and then the coin is only under the influence of gravity, whereas he's accelerating upward into the coin. Of course, it's going to take less time to hit his hand again. But this is very strange because, according to the guy in the elevator, he's not moving at all. He says, I'm not the one accelerating. All those rabbits and turtles and squirrels that I see on the ground, they're moving away from me, and they're moving away at a faster rate every second. They're the ones that are accelerating. So he does his math exactly the same as he did before. He's not moving, he's not accelerating, therefore the difference in position is zero. He does his math exactly as he did before, and he says, ha, the time is 2vi over g, which is exactly what he said before. This is a problem. This is a problem because either they don't agree on how long it takes for the coin to go up and come down, or they don't agree on what g is. The guy on the right, view from the ground, g is just the acceleration of gravity due to the Earth, 9.8 meters per second. But for the guy on the left, if he measures the same time as the guy on the right, he's going to say that his g, the acceleration due to the Earth, is 9.8 plus a. That's the only way to make those two times the same. That's very strange. And you might say, well, obviously the guy on the right is correct, because if the guy on the left looks out of his elevator and sees all these turtles and squirrels doing this crazy stuff, he'd have to conclude, no, I'm the one that's moving. So let's eliminate all that. Put him in an elevator in outer space, right? Let's say that he started out on the Earth, but I don't know, his friends were angry at him and they put some knockout gas inside the elevator. And when he wakes up, he can't see outside the elevator and he has absolutely no idea where he is, but he repeats this experiment. And he sees that the time it takes is this, and he decides, based on that, that the acceleration due to gravity, g, is 9.8 plus a. Well, he's got two choices. He can say, okay, I'm accelerating upward, or my friends have put me on an alien planet where the acceleration due to gravity is different than it is on Earth. This may strike you as ridiculous, but if you're trapped in an elevator, you really have no way other than looking outside to determine which one of these is true. And in fact, there's a name for this. It's called the principle of equivalence. There's no way to distinguish between a gravitational field and an accelerating reference frame. And this concept gave this guy a huge headache. He actually did this Gedanken experiment, he called it. Gedanken is German for thought experiment. And it gave him a big headache because his prized theory of special relativity only works in non-accelerating reference frames. But if it turns out that a gravitational field is indistinguishable from an accelerating reference frame, you can't do special relativity in a gravitational field unless you figure out how to do things in a non-inertial reference frame. It took Einstein another 11 years to fix this problem, but that is a story for another time. I hope this gives you an idea of what we mean when we talk about relative motion.